All right. Hello. My name is Giovanni Viscarando. I am the second student for the project two in fundamentals of aerodynamics. I'm just going to hop right in. So this is the data that I got from my partner, Tyler, from his simulation. So on the first sheet, we have our velocity profile at x equals 25, x equals 50, x equals 75. Again, these are supposed to be in centimeters. And then these are the wall fluxes. So the has the shear stress and the skin friction coefficient. Um, so here we have both of these things. I'm sorry, give me 1 second. All right. So first, what we're going to do is we're going to create a new sheet. All right. We're going to call this one our, not there, sorry about that, our theoretical calculations. And on the sheet, what we're going to do is we're going to calculate the values we should be getting, and then comparing them to what ANSYS Fluent gave Tyler. Um, so yeah. So the first thing we're going to start off by doing is we're gonna have constants. All right. So I'm just gonna create a small little thing over here because our main thing is going to be in this area. I'm just gonna have our constants over here. I think it should be far enough. I'm just gonna write constants. All right. We're gonna bold that. Nice. The first one we're going to have. 1 second. We're gonna have our density, which is p. So I'm just gonna go here and we're gonna use the symbol for density. Let's make it look a little bit nicer. All right, here it is. So, okay, nuclear density equal to 1.2, which is uh, given in the problem. Um, and then we have. So I'm just looking at the problem right now. Our velocity u or u infinity u and subscript. I just want this to look nice, which is why my table infinity insert excellent. And again, equal to 2 meters per second, but I'm just gonna leave it as 2. Our viscosity, uh, mu, which is equal to 1.8 times 10 to the negative fifth, plate length of 1. Don't really have to do that. Okay, then we have our constants, and then give me 1 second. Um, yeah, that's all we need for our constants right now. I'm gonna go back to the problem really quickly on my other screen. Okay, and then so first you have to find the boundary layer thickness, right? So boundary layer thickness is going to occur when little u equals 0.99% of big U, and maybe make it look nice. Maybe. Um, and then since U is equal to 2, we have 0.99 times 2. Oops, sorry, that's nonsense. Which equals 0.99 times 2, which equals to 1.98. Sorry, 0.98, which is, easy enough. Um, so what we're going to do now that we have that is we are going to go to our velocity profile and find where velocity equals 1.98. So we're going to do what we have here, boundary layer, node, and then when x equals 25 centimeters, when x equals 50 centimeters, and when x equals 5 centimeters. We're going to go down here because this is our velocity. Again, we're looking for 1.98. Go down. Here is the closest thing we have to 1.98. Okay, yeah, it's 5. So we're going to have that there. That's 5A261. We'll go up equals A, oops, A261. Do that. Then we're going to go down here, find the yellow. Yeah, I accidentally did this before. But again, this is the closest thing to 1.98, and that's going to be D319. Excellent. And then we're gonna look for 75. 1.9 is right around here. Gonna be the closer one. So it's gonna be 1 point right here. No, it's G355. It's going to be G355. All right. Now we have the boundary layer for each location. And now what we're gonna do is we're gonna make a velocity profile graph. So what we're going to do is we're going to take do this, 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 all the way down to the bottom. It's gonna take a little while because we have a lot of data sets. We have about 1,000 data sets. Now slowing down when you're at the bottom, we're right there, and we are going to add them to the line graph. This, we're gonna copy this. And hopefully that works. Bring it to the top. There we go. So this is going to be the one for the first one. We are going to now right click, select data, edit this. We're going to call this x equals 25 centimeters. Okay, on that, we're going to add one. Actually, cancel. Go here, hit edit. I'm actually just going to copy this. It's going to be the same for all of them, except the letter's going to be different. So I'm going to call this one x equals 50 centimeters. And then I'm just going to paste that there, and then change that from A to D. D, D. And then do the same thing here, but change that to E, E, E. And that looks good. We're gonna hit OK. Then we're gonna add another one. We're gonna do x equals 75 centimeters. Then we're gonna paste again. And this time we're gonna change it to G, 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 and then paste again. Change A to H, H, H. Hit OK. Now that we have all three of our data sets, we're gonna hit OK. And there we have our graph. So now we are going to make the y-axis. Oh wait, first we have to add these things. We're gonna add axis titles, and we're gonna add a legend just to make things a little clearer. So here we're gonna have our y, and then here we're gonna have our velocity, velocity, velocity. There you go. Well, actually, we're gonna call y distance from point. Distance from y. And let's include the meters, and then here let's include right, and then we're gonna name the title velocity profiles along flat plates. And there we go. We have our velocity profile graph. Excellent. Um, okay, good. Velocity profile graph. See, boom. They're all relatively similar. Now we're gonna go back to our. We're gonna need this in a little bit. In our theoretical calculations. Right now we're just gonna create another table. We're gonna have bold as x in meters, x in meters, and then next to it we're gonna have our Reynolds number, our Reynolds x, and then subscript, make it look nice. X, okay, and then we're gonna bold that. All right, excellent. Here we're gonna have 0.25, because again it's gonna be the same thing, 0.25, 0.5, and then 0.75. I kind of did this out of order, should have done that now. But we're gonna add another thing over here. We're gonna call it equation. So here are Reynolds equations, RE. This is the only way to do it. Equal to, I'm just gonna copy this. We're gonna do equal to, let's see, rho rho u, rho u x divided by mu. Fill that out. It looks nice. All right, that's going to be our equation. So over here to find the Reynolds number, we are going to do our mu, which is 1.2. We actually do it up here. 1.2 times our u, which is 2, times our x. So in this case, it's going to be this one. Okay. Oh, wait, that's what I forgot. Equal sign. Equals times that, right? It's going to be all of that divided by our mu, which is 1.8 e to the negative fifth. And then in parentheses. All right. Oh, all right. And we're going to hit click. And then we're going to drag it down. And those are our Reynolds numbers for each part. Excellent. Now that we got that. Now we're going to calculate the theoretical boundary layer. So we're going to insert the symbol, this, insert uh, theoretical. Okay. So fold this. That's okay. And then for this, our equation is going to be mu equals, once we rearrange the equation, it's going to be 5x divided by, I'm not sure how to square root, so I'm just going to do uh, RE x to the power of 1/2, which is the same thing as the square root. Um, this, this, parentheses, so you know what I'm talking about. Um, so in the Excel formula, theoretical is equal to, actually, I'm going to move this over. Theoretical. This on the equation is going to be 5 times A2, sorry, A2 divided by the square root of B2. What was that? And boom, that's the number we should get. And we're just going to drag that down. Now we're going to find the bound. Now we're going to use the boundary layers that we found before. So I'm just going to take this. Let's see. Three. I'm going to call this one fluent. And this fluent. Fold, fold that. And then we are going to go back to our velocity profile and pick this. I'm just going to scroll down, select on the yellow. Yep. Control C. Theoretical calculation. C. Sorry, wrong one. Go down. We'll see. Browser. Here. We'll see. And then go back. Go down. Oop, I like, see. So as you can see, our things are pretty wrong. Again, I didn't make, I didn't, this isn't my data. This is, so, and then we're gonna do message error, and let it bold it by itself. Yes, it will. Excellent. And to do the percentage error, we're going to equals the absolute value of this. Oh, sorry, we actually need to do of this minus this. Those are parentheses divided by this parentheses times 100. And as you can see, we have a pretty high percentage error. Um, but we didn't know how to fix that. So that's just going to stay like that. So yeah, that's the difference between error. Probably something with the slip conditions, or I'm not sure exactly what it could be. But now that we have that, um, we compared our boundary layers. We're going to find the in friction coefficient. So again, we're going to go back to our equations. We're going to see equal to 0.664. Turn off the subscript. Buzzer equals 0.64 divided by, again, RE x x to the, you guys saw that one, to the power. Um, again, now we're going to do C. That's theoretical. Just copy this. So for theoretical, we are going to do 0. Oh, wait, actually, sorry, up here equals 0.644 divided by the square root of the Reynolds number for that one. So for this one's going to be this. There we go. And let's get bring that down, bring that down. Now let's go see what Fluent has for us. Fluent, there we go. Go down so we get to 7.5, which is right here. Again, we are very far off from. Go there and expand. Oh, sorry. This goes here. Scroll down so we get to 0.5, which is right here. Leave that and put it here. And I don't know why the thing changed. And then we're gonna go down to 0.5, which is right here. And there. Change this to match. And match is better. All right, there we go. And then we're going to do percent error again. All right, and again, this is going to be equal to the absolute value of this minus this, parentheses divided by this, parentheses times 100. And I think we're going to have a really large percentage error here. Yeah, this is really bad. But again, not my data set, but yikes, not what we should be getting. Finally, we have that we're going to do our shear stress. Our shear stress is going to be tau wall. I'm not going to probably do the subscript that time. This is equal to 1/2 of mu u squared mu squared. See, I'm not going to bother this subscript right now. And this is the wall shear stress. Well, actually, I'm going to move these over just like 2. I'm going to move this. Okay. Sorry about that. Now we're going to do our mu stress. That reticle. And then is that out? I don't know why that didn't bold, but there you go. And now for this equation, we are going to do equals 0.5 times our density, which is 1.2, times our u squared, times 2 to the 2, and then times our CF. So we're going to continue using theoretical. This will be H2. Type yeah, my bad. I forgot to do the times. Down. Okay. Um, regime. Yeah, that's fine. Then we were going to go from the fluid tables up 7, 5, right here. Copy there. 5 right here. There. 5 here. Oops. I just messed up. Sorry. Hold on. No one should be right as 0.5. So, let's see. There. Right. Okay. Then 0.75 here. No. Sorry. Then we're going to finish this again. Matches. We have that. On the percentage error again. Uh, this minus this. Close parentheses divided by this. Close parentheses again. That's this time our percentage error still kind of high. Oh, no, actually our percentage error isn't that bad. Um, that's the only one that looks correct. But yeah, I'm not sure what's going on with this. But now we are going to do the skin friction graph. Select these and select skin friction right here. We're going to use our theoretical values and we're going to insert graph just like that. Excellent. That's right there. Okay. X. And then we just add the other one. Door. Boom. Boom. Add another one. Difference. Use X value. Same. Y values. Identity. Okay. Okay. Add X legend. Then that one is going to be our Y. Going to be our EF. And then the title is going to be in in uh, efficient, sorry, long wait. Just so you can, just so you can see the comparison. And then boom. And we're gonna need the wall shears graph. We're just gonna do the same thing. X, reticle graph. Yeah, it's kind of similar, but um, um, yeah, add, yeah. And the X value is just gonna be this, Y value this. Okay. See, they're pretty close to each other, unlike this one. Axis title and legend, axis, X axis, so X here, here, wall here. This is what we can call um, um, part title, wall, wall here, stress on, on the plate. Um, there we go. And then, oh, we have to find the, now we have those, we have to find the drag coefficients. Move this over here. We have to find the plate Reynolds number, right? Plate Reynolds number, we're going to call that um, uh, the length of the plate, I forgot to mention, one, right up there. And then the Reynolds number, that's going to be kind of similar, except instead of X, it's going to be L, right? For that, we're just going to do to 1.2, 2, 1, not divided by 1.8. That, and that's what we get for RE. Now, now the drag coefficient, CD, um, rearrange the equation, equal to 1.328 divided by RE L power half, and then you have to square root it. So, because it's really 1.328 over the square root of REL. I'm just gonna write that there because I'm not sure how to do that. We're gonna get that AD is equal to 1.328 or 1.328 divided by the square root of this, which is equal to 0.0367. I'm actually going to put this, we're going to rearrange this, sorry. There, REL, that, that, this, here. And that is basically it. Let me make sure. Um, yeah, so going back to the first one. Here's scroll up. Here we have our velocity profile graph with our boundary layers, very similar. Then for our theoretical calculations, um, we have our x, we found our Reynolds number for each, our boundary layer theoretical, and the one for fluid, and the percentage error, the skin friction coefficients for same thing, theoretical fluent for our wall shear stress. Then we put them in the graphs, and then part D we did right here, where we found the plates, the Reynolds number for the plate, and then we found the drag coefficient for that. I don't think it gave me the drag coefficient. Oh, I guess that would be what, at 1 right there, right here. Um, Again, that doesn't look exactly right. Um, Sorry, this is becoming a bit of a mess, but our theoretical medical ED this. Oh, sorry. Here. We'll go with this, and then I guess our fluent, or sorry, CD theoretical compared to our ED fluent is going to be this, I guess. Um, Actually, hold on. Um, yeah, I'm assuming. No, I'm actually not sure. I don't believe he gave a fluent. Um, Hold on. Give me 1 second. I will be back to find out. All right. Hello. Sorry about that. I was able to find the coefficient from the from the fluent. My partner had it. I'm just gonna copy this and put it here just so you can see it. Or put it over here. Make it a little bit bigger. Right here, it says the coefficient is 0.01678. So again, that's not technically what we have. Um, but sorry, give me 1 second. Okay. So the total is right there. So we're gonna do CD. Pretty sure I had CD fluent in here, right? Doesn't matter. CD fluent. All right, and then we're gonna do bold, and then we're gonna put in 0.01678. And then the error, that error is going to be, and then we hold that. That is going to be equal to value of this minus that divided by that, and then times 100, and we're getting a pretty large percent error. Yeah. So there's going to be the percent error right there. Large percent error. Again, something was wrong with the simulation. We couldn't figure out what it was. So yeah, that's I believe that's it. That's all the things I needed to cover in this video. So yeah, thank you for listening. Bye bye.